Assalamu alaikum everybody, and welcome to our demonstration of the CPI item level price curve movement network. For this project, we applied discrete graph theory to Pakistan's consumer price index to visualize how inflation spreads between different items across multiple cities over 3 years. We observed the similarity of consumer items based on their price movements pattern across multiple cities. We considered two items to be adjacent if large number of cities exhibit similar change in price. And the data we used was from 2023 to 2025. We calculated the cosine similarity between the 11-month price change vectors of every single item. If the vectors point in the same direction, meaning the items rise and fall in price together, the similarity approaches to 1, and the similarity approaches to 0 if the vectors do not point in the same direction. In this slide, we can see all the visual comparison of different thresholds, which affects our graph. At a low threshold like 0. 0.6, we can see the graph is a bit chaotic and it doesn't make sense because the weak correlations are allowed in this graph. But as we increase the threshold to 0. 0.7 and 0. 0.8, the network actually strips away all the noise, leaving only the most strong economic links. We can see from the sensitivity curves that this proves our last statement mathematically. As we tighten our parameters, the total number of edges we can see drop actually rapidly, proving that only a core group of items experience a synchronized inflation worldwide.
The first scheme is city count, where edge weight equals the number of cities that experience the price sink. Thicker lines here represent national breadth. The second scheme is average similarity, where weight equals the actual cosine score. Thicker lines here represent intensity, even if it only happened in a few cities. Because we use weighted centrality, these schemes completely change our item rankings. As you can see in the comparison chart, an item might have a blue bar, meaning its price movements are a widespread national phenomenon. But a smaller orange bar means that the mathematical correlation wasn't as intense. This is our category connectivity matrix for 2025. What's fascinating here is that the darkest boxes representing the highest price synchronization are mostly off diagonal. For instance, the strongest link of the year with 21 connections was between non food essentials and oils and sweeteners. This mathematically proves that inflation wasn't isolated to specific food groups. The price shock spilled over and caused contagion across entirely different sectors of the economy. Meanwhile, sectors like clothing remain almost completely disconnected from this network.
When we plotted the centrality stability of our top items, we discovered a massive V-shaped collapse in 2024. Our mathematical model proves that the normal synchronized inflation patterns completely broke down due to economic shocks that year, before restructuring and recovering in 2025. This temporal summary chart confirms it. We categorized our edges to see which correlations were persistent, surviving all 3 years versus transient, connections that were just 1 year flukes.
Looking at our code, we first made a data handling function that handled all our data accordingly and made up price change vectors. And the function which states compute price change vectors is actually the foundation of our project. Calculates the month to month change for 11 months and stores it in a sort of an array called a vector using NumPy, the library of Python. The cosine similarity part of our code is very simple. It takes two items, calculates their cosine similarity score, and then loops through every single city to aggregate those scores. And it matters because this script decides if two items are actually linked, and it sort of acts like a massive filtration system like we saw before in our slides, and it drops millions of weak data points and only keeps the correlations that pass our thresholds. For the centrality part of our code, it runs algorithms which are degree closeness and betweenness over the graphs to rank the nodes. Because we updated it, it calculates weighted centrality by converting edge weights into distances, which we can use further for our slides. The temporal analysis function is actually really interesting. It uses Python set operations like the ampersand and differences to compare the list of edges from all our data from 2023 to 2025.
To wrap up, what did this project actually teach us? First, applying strict discrete threshold filters out economic noise to show us the true backbone of inflation. Economically, we proved that inflation is a contagion. Our matrices showed that a shock to utility spills over and drags up the price of bread and grains. We also saw how fragile these networks are, with the 2024 data proving that extreme economic events can completely break down normal price correlations. Ultimately, this project demonstrated that discrete structures isn't just abstract math. By combining graph theory, centrality metrics, and partial orders, we can effectively map, measure, and understand the complex realities of our economy. Thank you.